Welcome back students once again to my video. This video is in continuation with the previous video. You can check the previous video if you are not seen. Okay students. So this was in continuation with the previous video. We are discussing photoelectric effect. The basic things of photoelectric effect have already been explained. Next we have to consider the famous experiment which is Hallwalks and Lennard's experiment. It's known as Hallwalks and Lennard's experiment. This is an experiment to systematically study the photoelectric effect. Okay, so what is being done here? You see, students, a discharge tube is taken, a hard glass discharge tube is taken, and there is a provision to evacuate it so that air is pumped out, and also there is a provision to allow certain light of desired frequency and desired intensity and desired color to enter here. Now there are two platinum electrodes. You can see students, platinum electrodes are there. One of the electrode is coated with the photosensitive metal. This is the photosensitive metal. Photosensitive metal. This is a hard glass tube which is known as discharge tube. And this is connected to a voltage supply. Okay students, this is connected to a voltage supply by means of a commutator. Here we have a commutator, I have not shown here. Okay, so by means of commutator you can interchange the polarities of this. So right now, as you can see students, that positive potential is applied here and negative potential is applied here. So you can call this as cathode or the emitter. Cathode or the emitter, because it will emit electrons. It will emit electrons once it receives incident radiation of suitable frequency. And this will be known as the anode because it has been maintained at positive potential. And also its purpose is to collect the photoelectrons reaching here. So we call it as collector. So it is denoted by A, collector is denoted by A, and emitter is denoted by C. C for cathode and A for anode. Right. So the electrons, they travel from cathode to anode, thereby completing the circuit, and externally you can see the circuit is being completed. Now here we have one ammeter here and a voltmeter here. Okay. I have not shown a two-way switch here. There will be a commutator which is a two-way switch. This facilitates interchanging the polarities of the cell without disconnecting it. That I have not shown because it's unnecessary confusion. Okay students, so we'll understand the experiment very simple, in a simple manner. Light of suitable frequency is made incident on the photosensitive metal. You can see it has been shown with red color, photosensitive metal. This photosensitive metal starts ejecting electrons, which are nothing but the photoelectrons, and these photoelectrons are sucked or attracted by this anode because the anode is maintained at a potential relatively higher than that of cathode. You can see positive terminal of the cell has been connected to this. So this has been maintained at higher potential relative to the cathode. So this way the electrons are attracted towards this and the circuit gets completed and a current flows. So that current will be known as photoelectric current. That will be measured by this ammeter. You can see there's an ammeter here. So it is to record the photoelectric current. Also you can see students, a voltmeter has been connected between the two electrodes, that is cathode and anode. Okay, between the emitter and the collector, this voltmeter measures the voltage. We can call this as the anode cathode voltage or the emitter collector voltage. You can call this. And also there is a provision, you can see, to change this value of voltage by shifting this point of contact here. We can increase or decrease the potential difference. Also, as I told you student, I have not shown a commutator. A commutator will be there which will facilitate the interchanging of the polarities of the cell. Okay, that means anode could be given a relatively negative potential related to cathode if required. So I hope that is clear students. This is the experiment. Now we have to understand there are 5 parameters which have to be understood properly. Okay, so the first parameter is this. So what are the parameters involved here? Related to this incident light, related to This incident light, you have its frequency and intensity. These are the two things. One is the frequency and the other is the intensity of light. Then related to the photosensitive metal, related to the photosensitive metal or photosensitive substance, you have what is known as work function. Okay, and then based on the experimental arrangement, you can see we have photoelectric current and anode cathode voltage. We have, this is the third one, and we are seeing the fourth one, that is photoelectric current. Photoelectric current, and the fifth one is the voltage between emitter and collector. These are the five things, students. So frequency will be denoting it with F, intensity with capital I, work function with W. In certain textbooks they take it as 50. Photoelectric current I denote it by I, and voltage, anode cathode voltage or emitter collector voltage as V. These are the five things involved here, students. So we have to seek relationship between these five parameters. Okay. So one by one we'll see what all things come up along our way. The first thing is we'll be seeing the relation as well as graph between photoelectric current and intensity. Okay, students, photoelectric current and intensity. So now see, try to understand. Rest all the things are fixed, of course. V is fixed, frequency is fixed. Okay, photo metal is fixed, so work function is fixed. Okay, and of course the anode cathode voltage is also fixed. The potential difference between the emitter and collector. So in such case, what will happen, students? See, we are assuming that the frequency is above the threshold frequency. Okay, in certain books they denote frequency with nu also, not a problem. We can denote it with nu also. Okay, so here, assuming that the frequency is greater than the threshold frequency, we can observe the photoelectric effect naturally. So here, intensity, based on the intensity, the number of photons striking the metal surface is fixed, isn't it? Based on the intensity, that is, intensity decides the number of photons striking the photosensitive metal per second. So based on that, every single photoelectron which comes out is the result of its interaction with one photon. Okay, and the number of electrons crossing any section of this discharge tube is a measure of the current, because current is after all the rate of flow of charge. So if we increase the intensity, we are actually increasing the number of incident photons per second on the photosensitive metal. So naturally, there are more chances that more number of electrons will be ejected, because every single photoelectron is the result of collision with one photon. So if we are increasing the number of photons striking per second, number of photoelectrons will increase. So rate of flow of charge will increase. So obviously the electric current will also increase. So based on that, we can write this. That is, intensity is something which we can control, and photoelectric current is accordingly we have to show. So this will be directly proportional graph. You can see, because increasing the number of photons per second, number of photoelectrons ejected per second will also increase, and they will be direct proportion. So therefore, current is proportional to intensity. I hope that is clear. Right. So then coming to the next graph. Sorry. We'll see the graph between current and anode cathode voltage, photoelectric current and anode cathode voltage. Now you see, students, this is the voltage, anode cathode voltage, and this is the current. Okay. Now if there is no voltage, that is, if we simply connect the emitter and the collector with a wire simply without any potential difference, still we can see that the ammeter will show some reading indicating that a current is flowing in the circuit, even though there is no apparent potential difference between cathode and anode. How is it possible, students? Naturally, the photoelectrons ejected will be coming out with certain kinetic energy, and this kinetic energy may be adequate enough to make them reach the anode. So this way, within the discharge tube, the electrons keep moving from cathode to anode, thereby completing the circuit. And outside anyway, you have the wire and electrons are there outside. So this the circuit gets completed and current starts flowing. So you can expect a non-zero current when there is no potential difference. Then, as you increase the anode voltage, positive anode voltage related to the cathode, more and more electrons will be attracted, students. So naturally, the rate of flow of charge will increase, so current will increase. Till a stage is achieved where almost all the photoelectrons ejected per second are being pulled away by this anode. Suppose, as an example, let us say in 1 second, 1000 photoelectrons are being ejected. And if in the same 1 second, all the 1000 photoelectrons happen to reach here, then we say saturation current has been achieved, and you cannot expect any more increase in current unless and until you disturb this incident light, unless and until you change this incident light. In that situation, simply by increasing the anode cathode voltage, you cannot expect any further increase in the current. So such a current is known as saturation current because it has been saturated. Alright, students. Then now suppose we reverse the polarity of the cell. As I told you, there is a commutator which facilitates this reversing polarity mechanism without disconnecting it. So now the anode is kept at a negative potential related to the cathode, or the collector is maintained at a negative potential related to the emitter. So the electrons will be repelled away. Electrons will be repelled away. So less number of electrons will be able to reach the what we call emitter, and accordingly the current will reduce till you apply a certain potential in the reverse sense, that even the most energetic electron is not able to reach the collector. So automatically what happens? The current reduces to zero. The current reduces to zero. So this potential is known as stopping potential. We have already discussed this in the earlier video. It is the minimum potential required to be applied in the reverse sense. Reverse sense means the collector should be maintained at negative potential related to the emitter. Then that minimum potential which makes the photoelectric current zero is known as the stopping potential. Okay, students, this is the graph, and that is clear, I hope. Alright. Now, suppose we change the intensity. We keep changing the intensity and then we keep drawing this graph. Okay, here what we are doing? We are fixing the photometal. So photometal is fixed means work function is fixed. Also we are fixing the frequency. Frequency is also fixed. Okay. Then for corresponding to each intensity we are plotting this graph. Okay, student. So let us say for a certain frequency, the graph is something like this. Let us say this is the graph. Okay, student. Let us say I1 is the intensity. So as you can see, this is the stopping potential. Okay. Then when you increase the intensity, what will happen? The more number of electrons will be ejected, and accordingly you can expect an increase in the current also. So saturation current also increases proportionately. Okay, students. But stopping potential will remain same because we have not changed the energy of every single photon, because frequency is fixed. Frequency will decide the energy of every single photon. Unless you disturb the frequency, energy of each photon remains same. Then further still we increase the intensity, again the saturation current will still increase. Okay. So here I have taken I3 greater than I2, which in turn is greater than I1. So you can see the stopping potential is independent of the intensity as long as the frequency is kept constant. Okay, students. Then we'll take up the next dependency, that is relation between, in form of graph we'll see, of course, between frequency and what we call voltage. Okay, frequency and voltage. Of course, we are plotting the same graph here, students, but this time we are changing the frequency and we have kept the intensity same. Same kind of graph we have. See. We are plotting the same graph again. Potential difference and current. Here we have kept intensity constant. So work function is anyway constant, of course, because we are maintaining the same photosensitimeter, and intensity is kept constant here. So we'll change step by step frequency. Let us say for a certain frequency, you get a graph like this. Let us say for a certain fixed intensity, this is the graph, and this is the stopping potential pertaining to a frequency, let us say nu1 or frequency f1. Next, we have increased the frequency. So automatically what will happen? Now we have increased the frequency, means energy of each photon will increase. So that means energy of every single photoelectron will increase. So they will be able to come out with more kinetic energy. So stopping potential has to be increased. However, since we have kept the intensity same, so you can expect the intensity to be same. So saturation current will not change, because after all saturation current will depend on the number of photoelectrons being ejected per second, which in turn will depend on the intensity of the incident wave. So saturation current will remain same. Is it okay, students? But the potential difference, the stopping potential for the second has been increased. Here, nu2 is greater than nu1. Then, still if we increase further to a new frequency, let us say nu3, then the stopping potential will be still more. So, assuming nu3 to be greater than nu1. So, this is how you get the current versus voltage graph. Okay, students? Then the next graph will be graph between Kmax and frequency. Rest everything is constant. So work function is constant because we have kept the photosensitive metal same. Intensity is constant. Okay, all these are constant. Now from Einstein's photoelectric equation, we can write Kmax is this, if you remember. So this is of the form, if you take this along y-axis and if you take plot frequency along x-axis, then it is of this form, y equal to mx plus c. Okay, it represents an equation of a straight line which has a y-intercept and also it has a slope. So its slope is what? Its slope is h. You can see h. H is the slope and intercept on y-axis is minus w. So minus w means it will cut the y-axis at a point below the origin. So this will be minus w. Numerically it is w. Okay, students. So this kind of graph. Here you cannot expect the graph to the left of this point because this represents the threshold wavelength, and less than threshold wavelength you cannot expect any photoelectric effect. So this zone must be greater than frequency must be greater than the threshold frequency. Only then you will be able to observe the photoelectric effect. Okay, students. Now this, as you know, this threshold frequency will depend on the work function. Suppose if you take another material, then probably its work function will be different. So accordingly, threshold frequency will be different. But slope will remain same. You can see, students, the slope, which is tan theta, is nothing but h. It's a universal constant. Okay, so you can expect other metal also. Suppose this corresponds to metal A, then you have for metal B with same slope, but probably some other threshold frequency. Okay. Now, in earlier videos we have seen that the Kmax will be E into V0, where V0 is the stopping potential. Okay. Then rewriting this Einstein's equation here, we can write E times V0 is equal to h nu minus w. Therefore, V0 will be h by E into nu minus w by E. So again, if you take this along y-axis, the stopping potential, and frequency along x-axis, then again you get an equation of the type y equal to mx plus c, which indicates that again it's a straight line. Okay, so straight line. So this is frequency, this is stopping potential, and again you get a straight line here. This kind of straight line you have. This time the slope is h by e. You can see h by e, and it's a universal constant. Slope is equal to h by e. This for, let us say, metal A. Then if you plot the graph for another metal, you can have another straight line with the same slope. Okay, same slope. But however, the threshold frequencies will vary. So these represent threshold frequencies, and the intercept on y-axis is this, below the origin. The minus sign indicates that it is below the origin. So this will be for the first, numerically it will be work function for the first divided by electronic charge. Similarly for the second, it will again be the corresponding work function divided by electronic charge. So this is how you get the different graphs, students. Okay, students. So I hope that is clear. Okay. Then before you solve numericals, you should understand one simple thing, that energy of a photon is h c by lambda. If you substitute the values, okay, if you substitute the values, h has 6.25 into 10 power minus 34 joule second, and speed of light in vacuum has 3 into 10 power 8 meters per second, and then finally convert this into electron volt, then you can write 12375 upon lambda in degree angstrom. You will get energy in electron volt. 375 can be replaced by 400 without any loss, without any error. So approximately you can remember this in this way also. So if lambda is in angstrom, 12400 divided by this gives you straight away energy of the photon in electron volt, and vice versa. You can interchange the positions of E and lambda. That is what I mean to say is that you will get lambda in angstrom if you divide 12400 with energy in electron volt. Also, we saw that work function is equal to hc by threshold wavelength. So this can be a formula for work function in electron volt is equal to 12400 upon threshold wavelength in angstrom. Okay, so this can also be changed interchangeably. This can be used here. Okay, student. And second of all, I told you that the energy gained will be charge multiplied by potential difference. If electric field does work in favor of the body, in favor of the movement of the body, then the energy gained, which is the work done by the field, will be Q into V. If the charge is going against the field, then it has to spend its own kinetic energy to do work against this. This formula is also very useful. In terms of electronic charge, if it is n times electronic charge accelerated through a voltage V volt, then the energy will be n into V electron volt. N into V electron volt. This can also be used as a shortcut method, students. Okay, students? Right, students. We'll stop here, students. Thank you so much for watching my channel. And if you like my channel, kindly subscribe this channel and hit a like button. Also, you can post your queries in this comment section. I'm free to answer you. Also, you may demand your own videos of your own choice. I'll definitely post it as I get time. Thank you so much.